All right, welcome back. So today we're going to be talking about topological sort. And yeah, first I'm going to go give a quick high overview of topological sort, how to do it and like what it means, and then we'll kind of hop into the problem. So yeah, let's just get into it. So okay, so yeah, this is the contents. So for our algorithm, we want to perform a DFS traversal from every vertex within degree 0, not clearing markings in between traversals. Record DFS post order in a list, and then topological ordering, it's given by the reverse of that list, reverse post order. So that may be kind of confusing on like what exactly that means. So I'm going to hop into an example and hopefully it'll make more sense. Cool. Okay, so we're given this tree and we're going to start at dash. And so yeah, we have this tree and let's just kind of walk through it. So our first thing we know is we're going to be doing DFS post order, and we're going to be breaking times by, let's just say, numerically. And so we'll go here first. We'll go to the 1, and so we'll visit the 1, and we want to notice that we don't add it to the queue or to our data structure yet, because we still have more places to go. So in this case, we're going to add the 1, and then we're going to go to so yeah, we added the 1 here. Sorry, let's go. And then we want to go to the B. So we visit the B. And then next, we're going to want to visit our exclamation mark right after. And we can see here that we have nowhere to go from the exclamation mark. And so in this case, we're going to add our exclamation mark to the queue. And again, we're going to go back to B now. And again, we have nowhere else to go in B. So we're going to add our B to the queue. Or sorry, B to the data structure. It doesn't necessarily have to be a queue. We can call it like an array. So yeah, so we add our B to the array, and then we, again, from B, we see how we got here, which we got here from 1. We see there's nowhere else to go from 1, so we're going to also add 1 to the array. The next thing we want to think about is now we go back to from 1, we got here from the dash, so we want to look at the dash, and because we know that there is still somewhere to go from the dash, we actually don't want to add the dash right away, and we're actually going to visit the 6. So yeah, we can see here that we visit the 6. And then from here, from the 6, since we've already been to the B, we can add the 6 because there's nowhere else to go. So we add 6. We go back to our dash, and now we can add our dash to the array. And so yeah, here we add the dash to the array. And then we're going to want to visit, we're going to want to start at C again, because we have nowhere else to go from the dash. So we're just going to go alphabetically. So we go C. From C, we're going to want to visit S. And then S, we want to look here. We only really have one place to go, so we know it's going to be M. This looks like this slide's a bit outdated, but this should be visited. This should be visited, and we should see here. So the tree should actually look something like this. I apologize for that, but so yeah, so the tree should look like something like this. So we can look at this, and we visited the M. We would have visited M in this slide, but it's clearly outdated. So we can say we visited the M. And then we try to go somewhere else from the M. We see there's nowhere else to go, so we add the M to our array. And then we're going to go back up. We're going to look how we got to the M, and we can see we got here from S. So we go back to the S, and it looks like this jumped a few steps forward. So yeah, we jump to the S, we go back to the S, and then we go, in this one, we would go to the C, and we would add the C. So yeah, that'd be the whole graph traversed. I'm sorry about these slides. A few mix-ups, but I hope there's no confusion there. Cool. So we can see here that we're going to get this post order that looks something like exclamation mark B16 dash MSC. And then when we want to do our topological order, we reverse the post order, so we get CSM dash 61B. So yeah, hopefully that made sense. And I'm going to be hopping into the problem right now to hopefully clarify anything else. And yeah. All right, so it says, suppose you were given this direct acyclic graph below. Perform a topological sort on this graph using the DFS post-order method discussed in lecture. Find a node with no incoming edge. Run a DFS post-order traversal from the node with no incoming edge. While there remain unvisited nodes, start a new DFS post-order traversal from any node with no incoming edge. A topological sort is the reverse of this order in which the nodes are visited. Break any types alphabetically. So I've kind of just put it here just to make it a little bit easier for everyone to see. And I'm gonna highlight the edges we visited to and like how we got there, because I think it'll make it a little bit easier. And I'm going to keep track of the edges we need to visit in a queue. Because remember, we're doing DFS. So we'd use the queue because that is how we do DFS. Okay, so cool. Let's just kind of hop into the problem. So we want to start off, and we start at I don't know. Okay, so I think we start at A, I believe. Sorry. Okay, yeah. So we'll start at A. Cool. Yeah, we'll start at A. Okay. So from A, we see here we want to add G, I, and E, or sorry, G and I both to our queue, because those we can both get from A. So in this case, we're gonna want to traverse G first because that's shorter alphabetically. So we want to take this edge, and then we can move to the queue. We hear here that we have H, so we add H to our queue, and then we're gonna pop it. So we'll take this edge to H because we can get there from G. And then we add B, we can get to from H, we can get to B. So we'll take this edge, so we pop it. And we can see here from B, we actually have nowhere to go. So in this case, we'd add our first element to our array, which would be B. So we're just gonna write result B. And this is because we have nowhere to go because we know this is a directed graph, so we can't take this edge. So we can see here from B, we got here from H because of my notation. So we want to go back to H. We want to look if we have any other places we can go. We can see here that there's nowhere else to go from H. So we're going to want to add H again. Cool. And similar story with G. We can see here that we have nowhere to go from G. So we're going to want to add G to our result. Cool. And then again, we're going to come back to A because that's the edge that's how we got here. And we see here actually that we do have somewhere to go. We can go to I. And we can also see this from our queue. And so yeah, we can go to I. Cool. And so from I, we can go to E. And that's it. So we go to E, take this edge. From E, we can go to F. And from F, we can visit G. But we already know that we already visited G. And so there's no point in visiting it again. So we're not going to visit G again. And we're going to say that F has nowhere else to go because we've already visited G. So we're going to add F to our result. So a little bit. Oops. Okay. So yeah, we had F to our result. And then the next thing we want to do is we want to see how we got to F, which we know is E. We can see here that we have nowhere to go from E. And so we're going to add E to our result also. Cool. And then the last thing we want to, or sorry, next we want to go is we have a similar scenario with I because we got to E from I. So we come back to I. We see there's nowhere to go. And so we're going to add I. And now we come back to A. And previously there was somewhere to go in A because we could have gone to I. But in this case, we're out of places to go. So it's time to add A to our result. Let me shift this over real quick. So yeah, now we had A to our result. And we go back to directions where it says, while there remain unvisited nodes, start a new DFS post order traversal from any node with no incoming edge. So let's look here. By the looks of it, we have D. You can clearly see that there's an incoming edge here. And B, there's also an incoming edge. But C has no, I guess you could say, like arrows pointing into it. So we're going to start from C. And from C, we can go to D. So we're going to draw this edge. And then from D, we can go to B. So we're going to take this edge. And then from B, we can see here that there's nowhere else to go from B. So we add B. And then a similar case with D, we come back to the B's parent, which is D. We have nowhere to go. And then now we're at D's parent, which is C. Nowhere to go. So yeah, and that's going to be our completed traversal. But the one thing about our topological cert is that it's the reverse of this. So it's actually going to be C, D, B, A, I, E, F, G, H, B. So yeah, hopefully that all made sense. And yeah, now we're gonna do problem 1.2, which asks basically what is the time complexity of the above algorithm? Give your runtime in terms of V, the number of nodes, and E, the number of edges. All right, so when we think about the time complexity of this algorithm, give your runtime in terms of V, the number of nodes, and E, the number of edges. So we want to think about how we would do this. And actually, the way we want to think about this is kind of maybe different from what you would initially think. Where we want to actually think about what we would do to set up this algorithm and initially run this algorithm. So we know the way this algorithm starts from earlier in the video is we want to find all all vertices that have no like pointers into them. So like something like C or A, sorry, no incoming edges. Sorry, I was missing the word. So the way we can do this is we first want to iterate through all the edges, and we want to keep track of the nodes that have in degree 0. And so doing that, it would take so after iterating through all the edges would take E time. So E iterate through edges. And again, this is gonna find the nodes with zero like in degree. And the next thing we want to do is we want to take all the nodes with in degree 0, and we're gonna want to push them on our stack. And in the previous video, I might have misspoken and said queue instead of stack, but we're gonna want to actually push the nodes with in degree 0 onto our stack, which is gonna actually take V of time because we have to iterate through all the vertices and know which ones to put on the stack. So it's gonna take V. Cool. So together, we're gonna know that this is gonna take O of E plus V, and hopefully that made sense.